Hello everybody, and happy Friday. I hope that you had a pretty good week. And I see that some people are surprised that this is on time. And what that means is that we have had some people here before. If you haven't been here before, welcome. As people know, I usually say what we're going to do here is what you're not used to, which is a math class where you get to ask the questions, not me. And what I try to do is I try to answer the questions in a way that is as understandable as possible to people who might be just learning algebra or geometry. Now, the questions that are asked can be all crazy kinds of things. They can be all over mathematics, or they can be about bananas. I'll always try to make some answer that makes sense no matter what happens. Okay, so let's see, what are we going to talk about today? Let me pull out the pen and find out. Okay, here's some geometry problem. Let's start with this and see what happens. This question is asked by Springfield Chinese at Sukanta Day. I'm not really sure who that person is, but nice question. The question is like this. So we happen to have a rhombus. A rhombus, what's a rhombus? A rhombus is spelled with an H. Rhombus. And a rhombus happens to have somehow all four sides of the same length. It's a four-sided shape. And this rhombus has the long diagonal is 3 times as long as the short diagonal. I guess I should draw a long diagonal and a short diagonal. And let's pretend that the long diagonal is 3 times as long as the short diagonal. Oh, here's how I can tell you I think that's sort of right. Because this half of the long diagonal looks like it's about 3 times as long as that half. Sort of. And then what I'll do is I'll connect them. And this is a rhombus. Okay? And the rhombus is saying, rhombuses don't talk, but the rhombus happens to have that the long diagonal is 3 times as long as the short diagonal, and the perimeter of the rhombus is 40 centimeters. Okay, so we got some information. So the perimeter equals 40. 30 would be ugly. Perimeter is 40, and what else we know is that somehow the long diagonal is equal to 3 times the short diagonal. That's this long one is 3 times the short one. And the question is, what's the area? Wow, people know already? 127? Oh, that's how many people are watching the live stream. I thought you were answering the question. Okay, so what we want to know is, what's the area? How do you figure these things out? Well, the way you try to figure this sort of a question out is you first try to say, I've got a perimeter, and I have a long diagonal and a short diagonal. And if I have a long and a short, then the long and the short of it is that we can just go and find out, if we can say that somehow, this little bit is an x, I don't know what it is, and this little bit is something else, 3x, then I could start to use the Pythagorean theorem and figure the whole thing out. That would be one way. But I'll show you another way I like to do it. I like to first of all pretend that I don't know this. I don't know anything about the perimeter. Instead, what I'm going to say is I'm just going to use the long diagonal as 3 times the short. So I'm just going to tell you, this is 3, this is 1, this is 1, and this is 3. Of course it's not true, because I haven't used the perimeter. But watch how I can make it true. So if I have 1 and 3, can anyone tell me what this is? We have to use the Pythagorean theorem, right? The Pythagorean theorem will tell us that this length here is the square root of, I see people have said 10. It's the square root of 1 squared plus 3 squared. A squared plus b squared equals c squared. And if you're curious about why this is true, there's actually a complete lesson on the Daily Challenge with Po-Shen Loh website, which we actually talk about. It's for free. It's like a 15-minute thing that talks about why this is true. So now that's the square root of 10. Okay. But that's not true. It's not supposed to be the square root of 10. What's it actually supposed to be? Well, there was this thing I canceled out. Let's uncancel it. So if the perimeter is 40, what am I actually supposed to have each side to be? Each side has to be how much? 10. Each side is supposed to be 10. So now here's what I'll do. I'll say that that was bogus. The side is square root 10. So what should I do to this rhombus to go and make a rhombus where each side is 10? I should take this rhombus and then multiply it. Multiply it by something. How much should I scale every side of it? Square it. Well, you can't quite square a rhombus. You don't really square the sides. You can multiply things by the same amount in every dimension, but you can't really square something. Instead, what you do, exactly what Winter Rain said, you take it and you multiply, you scale it by multiplying by the square root of 10. And if I scale it by multiplying every length by the square root of 10, then I will get a legit rhombus which has the right perimeter properties, and also it'll have the right long and the short diagonal properties. Okay? So now here's how I'm going to do it. I'm going to say, well then, let's just figure out what this area is, and then we'll know what the area is over there. What's the area of this thing? If I have 1, 3, 1, 3, what's the area of this thing? This is a rhombus. How would you find the area of this rhombus? The way you'd find this area of this rhombus is you go and say, well, I've got a bunch of triangles, right? Like this one over here. This one over here is just 4 triangles. And so it's just 4 triangles. It's basically half base times height times 4. So the area of this thing over here, this area, is equal to 4 of half the base times the height, which is 6. I saw some people say 6. And so the answer is what happens when you take something with area 6 and you scale it by root 10. And so the answer is obviously 6 root 10. Sure? Well, you've got to be a little bit careful. What happens to the area? If you scale something in both dimensions, then the area multiplies by that scale factor, and it multiplies by that scale factor again. Right? The way that it always works is that you always have to multiply and then multiply again. It's because if all I did was scale it this way, then of course I should just multiply by the scale factor once. But after that, I also scale this way, so I should multiply it a second time. And so what happens is that you actually have to have the area of 6 times root 10 factor this way times root 10 factor that way. So now the area is equal to 60 times root 10 squared. And that's equal to 600. Is that the answer? I hope that's the answer. We have some people here who, somebody said it's 6 because 3 times half times 4 is equal to 6. Seems reasonable. How many people here believe my answer of 600? I actually didn't come up with this question, so I don't know if that's the right answer. But we'll find out soon. Because I saw a lot of people putting different answers into the chat. So I'm not entirely sure whether or not people had thought the answer was something else. But it seems to be 600 because, you know, what we have over here. Wait a second. What are we doing? That's not 600. I can't multiply. Okay. As you have seen in all of these live streams, I am really, really bad at multiplying. So it's not 600. It's 60. That's much better. Okay. So no, absolutely not 600. If you take 6 times 60, wait. Why is there 60? That's why I got 600. It's because I ran ahead of myself. Because I was like, yeah, the answer is 60. This is what we want. Okay? Yes. So indeed, you have now seen that for me, doing this kind of calculation stuff, that's ridiculously hard. But on the other hand, the way that we can go and think about these problems is the best way to do it is to start with something which, you know, is easy to calculate. And after you've got something easy to calculate, then you just scale it by what you need. Okay? So in that case, the answer is 60, and I think we'll believe this one. Okay. Thank you, everybody, for pointing out that something was fishy. But I'll also tell you why I paused. Because I looked at this and I was like, really? 600 feels really big. Can you actually get to 600? I was like, I don't really think you can. And I'll tell you another reason why you can't. Because do you know which quadrilateral has the biggest area with a perimeter of 40? If I have a perimeter of 40, what's the biggest area I can make if I have to make a quadrilateral? Winter Rain's right. A square. And if you have a perimeter of 40 and you make a square, what's your area? Well, it's 10, 10, 10, 10. It's 100. So how in the world could you get more? So something was wrong. Okay, great. By the way, I want to move one of my screens because if you've noticed as I'm giving this live stream today, I seem to be looking off into the corner a lot. And that's because yesterday we were using this room to take pictures. And because of that, everything is a little bit shifted in the wrong place. So I'm just going to move a screen so that when I look at it and look at you, I'm actually looking right at you. One moment, please. And meanwhile, ask some questions. We'll pick one good one. All right, I think this will be better. Now I'll look more like I'm looking at you. What question should we do next? Tell something about your math circles. Well, as you know, I like to draw circles. I think what you're referring to is that there are going to be some talks coming up which are collaborations with math circles. Math circles are great organizations which are basically people who want to talk about interesting mathematics. And so that happens in many different cities all around the US. And we, these days, because they cannot meet so easily in person due to COVID-19, we actually run these sessions so that we can have something for them to come together and do. Okay. Yes, the Los Angeles Math Circle. I believe we're doing a collaboration with them really soon. More questions. Oh, okay. This sounds interesting. How many rotations will a small circle make when it rotates around a big circle? So you wanted to talk about circles? We've got circles now. So here's a big circle. Let's just go and make a problem. Circle. Okay? And let's give the circle a radius. Maybe this radius of this circle, it looks like 3. Now what we're going to do is we're going to take another circle with radius 1, and it's going to roll around. Okay? So we're going to make a circle which is like 3 times smaller. That was not a circle. But that's because I'm not very good at drawing my circles where they go around this way. We're going to give another go. Is that okay for a circle? It looks like part of a snowman. But now this one's going to be a 1. And now what we're going to say, it looks almost like it looks like one of those like Pac-Man things which is eating. Anyway, so we got this circle and it's going to roll around. So this circle is going to go roll around. And the question is, how many times does that circle turn when it's going all the way around? How many rotations? Well, how do we do this? Seems pretty easy, right? It's just that the ratio of the radii is 3, so it should be 3 times. Yes, exactly. The one looks like an eye. This looks exactly like that Pac-Man guy. I don't know if you guys played that video game, but the one where there's this ball and it can, oh, wrong way. It kind of goes around like this and it eats these dots and then there's these ghosts chasing it. It just looks exactly like a Pac-Man. But okay, so now the question is it 3 or is it 4? How would you think about this? Is this 3 or is it 4? It seems like it should be 3, right? Well, here's something that you can do to think about this. What is the answer if both of them had the same radius? Well, if both of them had the same radius, what ends up happening? If they both have the same radius, is it that it makes 1 rotation as it goes around? How would you even think about this? People are saying 4, this was an SAT problem. Well, how are you going to keep track of like what was this rotation? So the way to think about this, what is the question? The question is very simple. I have this little ball up here and it's going to roll around, and as it rolls around this whole shape, how many revolutions does this make? Double Pac-Man. Well, let's see. We can do this. We can say, see this point here? This is the bottom of the Pac-Man. When does the bottom of the Pac-Man touch this shape again? Right? So I've got this bottom of the Pac-Man. I'm not sure if you can see it. Let's give it a bigger lump. Okay, so that's the bottom of the Pac-Man. And when does the bottom of the Pac-Man come back into contact with this big circle? Well, it happens a third of the way along, because this bottom of the Pac-Man will start rolling around, and when this one rolls all the way around once, this one has gone 1/3 of the way around here. So if you have it rolling and rolling and rolling, that little bottom of the Pac-Man is going to touch the big circle again here, right? So it's rolling around, and here's the circle. And so it is at exactly this point that the bottom of the Pac-Man touches the circle. But when that happens, what does the Pac-Man look like? That's the bottom of the Pac-Man, the chin. So the Pac-Man looks like this. Is everyone okay with this? So what I'm saying is it goes from here to here. Now as it goes from here to here, this thing has gone around, and it actually has gone around more than you expected, right? Well, it has basically gone, it's not like it went from here to here where the Pac-Man was still like this. Do you agree? It's not this. It's not this. In fact, it's gone by a little bit extra. It's gone by an extra 1/3. I wanted to write the word extra, but that won't fit. Let's do it like this. Okay? So what I'm saying is that as you start here, a third of the way around, you somehow have gone not only to where the Pac-Man's mouth is where it was supposed to be, but an extra 1/3 also. So by the time you got here, the Pac-Man has made 1 1/3 rotations. Is everyone okay with that? Not one rotation, 1 1/3 rotations. Yes, there's a ghost. You're right. No, actually what's going on is that we have some people here who are helping to work and try to figure out how to make our app called Novid work better. But now we can see what's going on. When you've gone around 1/3 of the way, it has made 1 1/3 rotations. And if that's the case, by the time you go all the way, instead of 1/3 of the way, you'll make 3 times this rotations. So the answer, this is 1/3 of the way. When you've gone 1/3 of the way, you're here. So the answer is 3 times 1 1/3, which is 3 times 4/3, which is 4. And that's the answer. So this is a trick question. The trick question here is it looks like it should be 3, but no, it's 4, because as you go around 1/3 of the way, you've actually moved a bit more. Okay, more questions. Carbon News says, can you explain again? So the quick explanation, I'll just do it real quick again, is that, look at the Pac-Man. Here's the bottom of the Pac-Man. I guess it's like its neck. As the Pac-Man is rolling around, the question was, when is the next time that the bottom of the Pac-Man is touching this circle? Because the bottom of the Pac-Man is not glued to this circle. It's rolling. And as soon as you start rolling, the bottom of the Pac-Man starts to lift off from the circle, right? And it will only come back to the circle when it has moved along this circle the same distance as the circumference. It's sort of like gears. And so the circumference here is 1/3 of the circumference there. So you'd actually go 1/3 of the circumference, and then finally the neck of the Pac-Man is back down here. But if that's the neck, remember that the mouth of the Pac-Man is this way. So what that means is by the time that this rolls 1/3 of the way around, the Pac-Man's mouth has made 1 full revolution from here to here, but it kept going by another 1/3. So in that case, I know that in 1/3 of rolling around, the Pac-Man's mouth moved 1 1/3 rotations. So if you multiply together, when you roll all the way around, that's 3 of these things, you get 3 times 1 1/3, which is 4. Okay, more questions. Pac-Man. Sanjito asks, Sanji asks, do you eat bruised bananas? The answer is yes, sometimes. Especially if there's not a trash can nearby. Then it's easier just to eat the bruise. Okay. Oh, you might be wondering, why would there not be a trash can nearby? As some of you know, sometimes if I'm late for something or in a hurry, I might just, while I'm walking from one place to the other, go and just eat a whole bunch of bananas. It's very efficient. I've actually done this at a lot of conferences or meetings before, where maybe I woke up too late and I just quickly grabbed 3 bananas, and you just start eating bananas while you're walking to the building, and you basically throw away the bananas as you pass by trash cans. Okay, more questions. Somebody asked, will we have to call Evan Chen Dr. Chen when he gets his PhD? I mean, honestly, I think that's the respectful thing to say, but everyone's different. Everyone's different. Right. Somebody said, do you always have bananas around you? Bananas are very convenient to have around you, and a lot of events that I normally attend are on university campuses. And in universities, in the dining halls, they usually have bananas. Because bananas well, they don't keep very well. They all turn black. But you can just kind of leave them there, and, you don't need to get really messy while you eat them. Why are we talking about bananas? Is it because my shirt happens to be the color of a banana? I see. Somebody just said that I'm a minion in this shirt. I think we better go back to the math. Oh, neat. Moonwatcher123 has a puzzle for us. The puzzle says, use the numbers 1, 2, 3, 4, 5, and the symbols plus and equals. Make an equation. A true equation, not just any equation. Okay, how do you do that? Well, I have 1, 2, 3, 4, 5, I have a plus and an equals. We have a lot of people here who are pretty clever, so maybe we can figure this out. There has to be an equal sign. And also, we might be putting some numbers together. That might be part of it. Oh, I see it! Does anyone else see it? I see it. Sorry, I got excited, so that might have made your audio too loud. Oh, that's interesting. What you suggested is not what I thought of. 1 plus 4. Oh, that's so funny. Okay, so I like this. So, Prerak, you thought of something that I was not thinking of. You wanted to do... Oh no, did you just go away? You used 2 equal signs. You said that 1 plus 4 equals 5 equals 2 plus 3. That's pretty creative, okay? That's very creative. And I think creativity points go to you for that one. But I don't think that's actually what they meant, because whoever asked this only gave us 1 equal sign. So, in fact, the one that I thought of... Oh, wait. But no, there's only 1 plus sign also. I think this is clever. Yours is as good as what I was going to come up with, okay? What I was going to come up with was to say I'm going to smush some numbers together. Like if I go and smush together the 1 and 2, I can get 12, and that's equal to 3 plus 4 plus 5, because 4 times 3 is 12. Whenever I add 3 consecutive numbers, the sum is 3 times the average. So I'd say that these two are both legitimate answers. Is there an answer that only uses 1 plus sign and only 1 equal sign? My hunch is no. I'm looking at these numbers, and I don't really think it's that easy. If you only get 1 plus sign, it doesn't look promising. No, it doesn't look promising. The reason it doesn't look promising is because if I use a 2-digit number plus a 1-digit number, I won't be able to go to the next tens digit. I just can't. Like if I did 14 plus 5, I would still be in the teens, so it wouldn't work. So I can't do a 2-digit plus 1 digit. That won't work because I won't be able to change the leading front digit. So I would only be able to do like 1 digit plus 1 digit equals 3 digits? No. And what if I did 2-digit plus 2-digit equals 1 digit? Also no. So we have just proven that it's not... Oh, use exponents maybe. Wait a second. Joshua Wu, maybe. Now can we do it? Now maybe we can do it. Okay, suppose we get to use exponents. That's clever. I think this is fun to maybe think about just briefly to see if we can do anything here. So if I wanted to make... Oh, wait a second. Okay. Oh, yes. Yes, yes, 1 to the 23. That's right. You can do 1 to the power 23 plus 4 equals 5. I think this does it. Okay? Yes, 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 yes. Because I saw the 1. When I saw the 1, I was thinking, you can do a lot of neat stuff with the 1. With the 1, you can go and take it to just about any power you want, and it'll still be 1. So if that's the case, the 1's like, it's like the Pac-Man. The 1 can eat up all the other numbers. And so I was just like, is there anything I can do with just like something with a 1 plus? And there's lots of them. Okay, I'm not sure if this is what you meant the answer to be, but I will say that this is the most literal meaning, the most literal answer to this question, because the question only gave me 1 plus and only 1 equal sign. And thanks to the audience, thanks to Joshua Wu for suggesting, let's go and use exponents to go and solve the problem. All right, what else can we do? Oh yes, and I see there's lots of things you can do. You could have done 1 to the 2 to the 3 plus 4 equals 5. Or you could have done 1 to the 4 to the 5 plus 2 equals 3. Lots of answers now. Let's go and see another question. Oh, Leo Z has asked, how do computer crops work? Computers don't grow crops. Well, that's not what the question was. The question was, don't forget circle and special shape crops. Actually, computer crops are pretty easy. What's going on is that the way a computer stores a picture is that a picture in a computer is just a sequence of little tiny pixels, little tiny dots. It's almost like they drew it on a big graph paper. And if you just have a giant graph paper, you could imagine that every single one of those squares is a different color. You could have given like a graph paper to like a pre-kindergartner or like some little tiny little kid and said, hey, go color this thing with blue, go color this thing with red. And as you know, little kids only use Crayola crayons, right? I mean, they use like crayons. And crayons have discrete colors. Discrete meaning you get like the fuchsia crayon and you go and get the aquamarine, which the aquamarine is different from sea green. And you have all of these different colors, and you just basically have this bunch of different colors that you color into those tiny grid squares. And so the way a computer stores a picture is it basically has a big graph paper, and it says that one's that color, that one's that color, that one's that color. Now the computer has more colors than Crayola. Crayola only has like, 16 colors for the basic crayons, maybe 80 colors for the mega set. I think I once saw a 256 color Crayola thing. But the computer can actually store up to these colors, which are like 256 times 256 times 256 many, or something like that. Sometimes there's another times 256 for transparency. But in any case, that's a whole lot of colors, right? And so what happens is that the computer is just storing this graph paper. If you do a crop, all the crop is doing is it's just saying, please cut the graph paper. And that's it. So it just restores restores the graph paper in a way where it says, well, I'm just going to crop it. Now you might ask, how does a computer store graph paper anyway? Because isn't graph paper two-dimensional? So what actually happens is that suppose you had some kind of a picture, and suppose your picture happened to be 1080 and 1920. Hey, does anyone know why I chose those numbers? The reason I chose those numbers is because that's the resolution of the YouTube video you're watching right now, I think. So many people's computer screens are like this, and this is actually the dimensions of your screen. But what's happening is that inside the computer has just like this like big, long, one-dimensional list of spots that it can store information. That's called the RAM, the memory. And so the way this is stored in the computer is the computer basically stores the information about all of these in this order. It stores all of these in this order. What color is that particular graph paper thing? And after it's gone all the way around to this side, then it goes, loops back over here, and it goes into the next row. Does this make sense? It's basically that you go and take this long, you go and take this like two-dimensional thing, and you just go and pretend that you cut, and then you go and you put them all in order. TempID said the order actually depends on the format. You're right. So if you actually happen to have a file in JPG format, it's not doing this. JPG is a compressed format where the picture is actually stored in less bytes on your hard drive than what actually is the real information in the picture. But for simplicity, I'm saying the uncompressed picture is actually when you just store it in this way. And uncompressed pictures are very, very large. Now, in the JPG thing, it's quite different. But that's also why JPGs, if you zoom in, somehow they get blurry when you get all the way inside. Now, when you have something like this that's going on, the way that the cropping would then work is if you had everything going across this way, and then you do some kind of crop, and you declare, I just want this. Then what happens is that the computer recalculates, like as it just goes and says, all right, then please tell me what was here. And it just restores in this order, these colors. So it does some math. It does some mathematical calculation of which colored grid square in the big picture do I actually want as my 4,520th colored square in this crop. So it's basically just doing multiplication, addition, subtraction. I believe not really any division other than figuring out what layer you're in. But I'm trying to think, you probably don't actually need any, you don't need any, do I need any division? No, I don't think I actually need to use any division. Just multiplication and addition will do. Okay, more questions. What else do we have? Ethan Gung asks, what can you hold in your right hand, but never in your left hand? What can you hold in your right hand, but not in your left hand? You're close. Someone said your right hand. No, it's your left hand. That's a good one. That's a good one. So what can you never hold? What can you hold in your... I messed up the problem. Whatever I said. What can you hold in your right hand, but you can never hold it in your left hand? And the answer is your left hand. Excellent. Okay, more questions. Oh, Leo Z has asked another question. And this one's a more legit mathematical question. Is there a thing called the 2.5th root? Well, what would that mean? What would that mean to be a 2.5th root? Remember what a square root means. A square root means it is a number which, if you square it, then you get, the number you were looking for. So let's just give an exact example. What's the 2.5th root of 8? Is 8 a good choice? 8's a terrible choice, but we're going to do 8 anyway. What is the 2.5th root of 8? Well, what would that mean? That would mean some number which when I raise to the power 2.5, I get 8. It's x, where x raised to the 2.5 is equal to 8. Oh no! How would I try to figure this out? What does it mean to raise to the power 2.5? Well, raising to the power 2.5 means I square it and I multiply it by it to the power 0.5. That's one way to look at it. Another way to look at it is the 2.5th power is actually... I'm trying to think if this is the best way to explain. I think this is okay. It's basically, if I want to raise something to the power 2.5 and get 8, it's also a number which if I raise to the power 5, how much would I get? I'm actually looking for an x where if I raise the x to the power 5, I'd get 64. I think that's what people wrote, but people wrote x to the power 3 is 64. So I'm looking for an x where this happens to be true, and if I have an x for which this is true, so notice the way I'm talking about the logic. If I have an x for which this is true, that would then give me x raised to the power 5 is equal to 64. Okay, so I'm looking to know, is there any x which makes this true? If I actually found an x which made this true, then the x would make that true too. Because this is the square root, right? And in particular, as long as I found a positive x, that would be okay. Here you always have to be careful of positive or negative. You don't want to go and get something where you took the square root of a negative number. But it's irrational. I'm not saying that this thing exists, because I'm just saying, is there any number which when raised to the 5th power is 64? There is. It's not nice. But there is actually a number there. So what I should actually say though is, how did I get that 64? The way I got that 64 is 8 squared. Is that okay? So now what I want is I want to know what's the fifth root of 8. That's what I'll be looking for here. The fifth root of 8, what's that? Well, the fifth root of 8 is actually, the fifth root of 8 squared is actually the 1/5 power of 8 squared. And that's because if I take the 1/5 power of something and I multiply it by itself with a total of 5 of them multiplied together, then I have a fifth, like the 1/5 power, 1/5 power, 1/5 power, 1/5 power, 1/5 power, I get the first power. So this is the fifth root of 8. And so now what I find out is this is 8 to the power 2/5. So if you want to have the 2.5th root of 8, the answer is 8 to the power 2/5. So that's what it is. As you know, now that we've learned this, if you ever want to know what's the 2.7th root of, let's make up some number, 6, it's equal to 6 to the power 2/7, right? No, that's not the pattern. Actually, that's not right. I just wanted to emphasize this because it looks like I just took 2.5 and I took 2 over 5. But no. Don't try this at home. This is wrong. This is wrong. Don't do this. No. Actually, the way that this 2/5 came about, where did the 2/5 come from? The 2/5 was not 2 divided by 5. Where is the 2/5 from? How do you get 2/5 from 2.5? Suppose I have 2.7, what would I do instead, right? So what is the deal? So if I have a 2.5 over here, 2.5 is the you take a reciprocal. 2.5 happens to be 5 over 2. And so when I get the 2/5, that's actually the reciprocal. And of course that makes sense, because if I want to have the 2.5th root of 8, well, that should be 8 to the power 1 over 2.5. The same reason why the fifth root of 8 is 8 to the power 1/5. So of course it's the reciprocal. So this is not right. Don't do this. Lawrence-san, notice me. I have noticed you. Okay, let's keep going. And if I have this thing, it's 1 over 2.7. What's 1 over 2.7? 1 over 2.7. That's equals 6 to the power 10 over 27. And you can't simplify that. And it's horrible. But it exists. So that's what these mean. So that's how you can get like 2.5th root, 2.7th root, all of these. Okay. Dayit, don't notice me. But I already noticed you. Okay. That's a tough one, you know? Like if you say don't notice me, and I notice, now what am I supposed to do? Let's do some more questions. Oh, Wesley Wren. Wesley Wren wants us to go and try a very hard problem, okay? No calculators for anyone. Oh no, I have to count this thing. How many things are there? Yeah, okay. Wesley Wren. You want to say no calculator. No calculator. Very important rule. And Wolfram Alpha counts as calculator. And we're supposed to figure out 1, 2, 3, 1, 2, 3, 1, 2, 3 times lots of 3's. 3, 3, 3, 3, 3, 3. Whoops. 3, 3, 3. But the question is not to work this whole thing out. The question is, what are the first 3 digits? Okay, I think I know the answer. What are the answers? Does anyone else have an idea? The question is, no calculator. You can go and multiply stuff on paper if you want to. But there's actually a nice way to do this problem, and it's related to a problem we did earlier this week also. Use Desmos. Are you sure? And are you sure the answer is 369 easy? I'm not sure the answer is 369 actually. If I multiply it by 3, the answer is 369. But if you multiply it with 3 and you get 369, you also have to go and take the other 369. You have to actually add all this stuff up together. So you're going to get some weird stuff going on, right? It can't be 369 because if you did this whole thing and we did the whole like long multiplication, look, this one is 36. Whoa, what happened there? This is 369, 369, 369. And the next one is 369, 369, 369, and it goes all the way out, and then you add. And when you add, you're not going to get a 369 at the front. It's going to have all this weird carrying. So what's the right way to do this problem? I see some people have different answers now. We have 408, we have 410, we have 959, 408, which is some telephone area code in San Francisco, I think. What else could it be? Is it 410? Is it 059? Is it Ask Google? Just add. Well, let's see. Let's do it this way. The hint was we did something just like this. And what we did was where they were all 9s. Why don't we do the problem with all 9s instead? That was a lot easier. And you can do that by just taking the top number and dividing by 3. Right? If I divide the top number by 3, then I can multiply the bottom number by 3, and that's the same answer. Divide the top number by 3. As I was doing this problem in my head, I was like, yeah, 1, 2, 3 divides nicely by 3. 1, 2, 3 divided by 3. Does anyone know what that is? 4, 1. 4, 1. So what that means is that I actually have the same answer as, let me erase this stuff underneath. Let's use the green to actually say it, is the same as 041, 041, 041, let's put an O here, multiplied by 999, 999, 999. Okay, now how did we do that earlier? The way we did that earlier is we went and said, look, if I'm going to multiply by all these 9s, that's the same as multiplying by 1 with that many zeros, and then subtracting just the number itself, right? If I want to know this weird number times all these 9s, the answer is weird number times 1 with lots of zeros minus just weird number. And importantly, when I have this many zeros I put on, weird number, when you multiply by 1 with that many zeros, gets shifted so far to the right that you don't need to worry about it. Okay? So when I shift it so far to the right, my answer becomes, so I have 041, 041, 041, multiplied by 999, 999, 999, okay? If I want to multiply this, it is the same as the 041, 041, 041 multiplied by 1 with 9 zeros, and that happens to be, adding 9 zeros, 000, 000, 000. That's if I multiply it by 1 with 9 zeros, and then minus itself. Minus 041, 041, 041. Is everyone okay with that? That's all we have to do here. Because I just multiplied by 1 with that many zeros and then minus itself. And since I saw that there were so many 9s down here, I knew that we would get to shift this so far over that I don't even have any carrying or borrowing to really worry with. So now, importantly, 0 is not allowed as a first digit. So if you do this subtraction, what you'll see is you'll actually get 410, something else. And so that's the answer. So this is a nice question. Actually, the question at first looks like you might have to go and ask Wolfram Alpha or ask your Desmos or some calculator. But actually, it's not bad. And the reason it's not bad is because it was 333333333, which is just like 999999999. And then this is all you have. So that's it. Christine Chu said, Prof. Loh can't see this, I think. I see it. Let's see, what else can we do? More questions, more questions. Wow, you guys have asked a lot of questions. I'm going to roll down a little bit more. Andrew Wu has asked, can you explain the Chinese remainder theorem? That's actually a much more extended lesson. We actually have that in our number theory class. But I know from experience that to explain it properly takes a while. So it's not something that I can do so easily here in this live stream. And in general, if you go and look for any resource on Chinese remainder theorem and kind of read through it slowly, that's the best way to understand. Wow. How do computers calculate roots? That's a good question. I don't know. The reason I don't know is because even the question of like how do computers multiply numbers, it's not clear that they use exactly the same methods that we do. There might be more efficient ways. And with roots themselves, I would guess that maybe they use a certain method for calculating square roots. Square roots are very standard, and there's actually a way to do that. But if you ask a computer to calculate the 2.5th root, I have a guess that it in fact uses logarithms. So logarithms are something which are basically solving the question, if I had 5 to the power something equals 23, what's the something? Logarithms help you solve that. And so whenever you're calculating roots, you actually can use the exponential and the logarithm together to solve that. But that's a little bit beyond the level of this live stream, so I won't hit that here. Oh, Jesse Patrick asked, how do computers calculate anything? Well, computers have certain ways of calculating and or, and they can also store a number with just like these zeros and ones, that's the binary. And then they actually have ways to kind of push those electrical signals together so that somehow if both of them have signals at the same time, that's like 1 and 1, then it's like, that's called an AND gate. Then what goes out is like, it's only going to be 1 if both of them are 1. And you can send out a 0 if somehow, you can also make it so it sends out a 1 if either of them is a 1. And between the AND and the OR, you can actually start to encode all kinds of addition in, for example, base 2. And then once you have addition, then you can start building anything else that you want on. Not really. You build addition, you build multiplication, and so on. But that's electrical engineering. So I'll leave that to another expert. Susan Xu, have you played Turing Tumble? I have not, but it sounds like it's something to do with computers. It sounds like it might have something to do with a Turing machine, or things where you have information and you have like a sequence of information stored in memory. I don't know any more about that. Oh. Why are the solutions, okay, so this is FF688. Why are the solutions of a quadratic its y-intercept? I think you mean its x-intercept. But in general, if I have a quadratic, any old quadratic, what's a good quadratic? X squared minus 6x, plus 8 equals to 0. Hey, look, it's equals to 0. So what that means is if I graphed y equals x squared minus 6x plus 8, if I chose to graph this, then I'm just curious, when does y equal to 0? That's why. Actually, y equals to 0 is called the x-intercept. Okay? And in particular, if I wanted to actually graph this thing, it's going to be a parabola. It will look something like this. And it happens to go across. I drew it on purpose so that this one's at 3, and it's down by 1. Oh, I don't know. Maybe it looks something like this. Something like this. Not perfect. Not exactly the scale. Oh, I'm a perfectionist. Let's do this. Looks a little bit better this way. But so what I have is I have this particular parabola, and what I'm trying to do is I'm trying to say, when does the y equal 0? Well, if I want to know when y equals 0, I'm just curious, when does this parabola have y equals 0? That means when does it cross through the x-axis? So that's all. And in general, whenever you're trying to solve any equation, if you want to know when the equation equals 0, you just have to go and graph it as like y equals something, and check when it passes through the y equals 0, which is also the x-axis. More questions? I see there's a lot of people who want me to talk about trig ratios. The reason I'm not going there is because I'm trying to keep the level of this live stream down at the Algebra 1 geometry level. And there are lots of very interesting questions that can be asked that are really interesting and people will learn from at those levels, whereas trigonometry sometimes, if you haven't learned it before, it can all just seem very strange. Harry Liu asked, did Prof Loh gain 2,000 subs after the Chinese stream? I'm not sure. I actually don't follow the number of subscriptions. I just show up here usually late every day and start talking about math. So if you guys have been paying attention to that, then you're probably right. Puja Meti, your parents have 6 sons, including you. Wait, I gotta write this down. Your parents have 6 sons, including you. And each son has 1 sister. How many people are in the family? Oh, one of these trick questions. How do you do these things? I see all these different answers, and when you see all these different answers, it shows it's a pretty good trick question. We've got 9s, we've got 8s, we've got 7s, we've got a 14. What's the answer? Well, I'm gonna give it a go. I might be wrong. Okay? So I see 6. And I see it's including you, so I'm just gonna say, actually I should never cross out information on the problem, but I should say that's it for the sons. There's 6 of them, okay? There's 6 sons. Each son has 1 sister. Oh. That means there's 7 people altogether, right? Each son has 1 sister, so presumably there's 1 sister in the entire family. So that's 7, but don't forget your parents. So that's a 2. Okay, so I need to go and add 2 here, and this is 1 here. I would say 2 plus 6 plus 1 equals 9. Again, I'm not sure this is right, but maybe it's 9. I'll say I think it's 9. Yes, indeed. Somebody has said, isn't the dad also the son of someone? Yes, in some sense you should keep going all the way up, but then it's not very clear what the answer would be, because you just have to keep going up and up and up, and somehow everyone will be one family. Yeah, I see people are saying each son has 1 sister. So what's the English behind this? If I tell you that each son has a certain property, nobody said that that property can't be shared, right? So if I tell you something like each son lives at home, yeah, that's the best example, okay? Suppose I tell you each son lives in the house. Would you say that then suddenly there are 6 houses? No, you wouldn't, right? If I just went and said your parents have 6 sons, including you. Each son lives in the house. So I would say that nobody said it wasn't separated. Nobody said it was separated. Pooja, who gave the question, said 9 is the correct answer. So that makes me feel a little bit better. But the general way you interpret this kind of each whatever as a mathematician, if you ever see it in a mathematical paper, if you see each blah, 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 that just means, okay, if you focus your attention on that thing, that each, the statement over here is true for it. But nobody said anything about how the statement over here has to be different things involved for the different sons. In mathematics, each da 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 just means go and fix one of them, and then it's going to be true for that onward. Okay, more questions. XOXO, a study has asked, how old is Po? I actually don't remember. Maybe you guys can help me do the subtraction. Somehow my birthday is now on YouTube, not YouTube, on Wikipedia for whatever reason. It's actually true. So I was born in 1982, so there you go. People already figured it out. I'm 37. At some point in your life, you actually just lose track of how old you are. Oh, that's a prime number. Oh no, so I'm not going to be a prime number for a while. Okay. Let's keep going while we wait for the helicopter to go by. I see. Ayush asked, sir, please explain what are derived angles. I think what you're referring to are directed angles. Sometimes it's useful to go and say, I'm going to measure my angles, let's say counterclockwise. And it's useful sometimes in geometry to say if I have angle A, B, C, angle ABC, this one, whoa, that's a weird C. This one looks to be 45 degrees. But it's useful to sometimes be able to say that angle CBA is equal to minus 45 degrees. Where what you're saying is that somehow it actually matters which way you're going. And also directed angles are actually directed angles modulo 180 degrees, which is a little bit extra confusing point. However, the notion is that somehow whether you're going clockwise or counterclockwise, the sign will change, modulo 180 degrees. Oh no, typo always. Not sure what you're referring to. Oh, you're referring to typos of other things on the chat, because I also make typos or draw-os or whatever they're called when I draw here. New question. What else can we do here? Umesh Dubey asks, what does Professor do during weekend? I can tell you what I'm going to be doing this weekend. This weekend, we're going to be continuing to do ultrasonic work on the Novid app to go and improve it even further, because I have some new idea of something I can do with the analysis of the audio that we're doing inside. So, that's what I do on the weekend. Oh, and also I'll be doing a bunch of, I'll be doing like a live stream on tomorrow at 8 o'clock p.m. about something. It'll be some collaboration. I'm sorry that you're saying my audio is changing. I really wish I knew why. I will tell you one thing I had done. I'm going to bring down the volume a little bit. So I had turned the volume to full 100% on the software I'm using to send the stream out. And what I'm wondering is, when I get super excited, is it that somehow I go over the max volume and then it somehow cuts my volume in the future? That may be. Okay. I see that Susan Shree says, you have a class tomorrow. At the same time, always have to watch it, not live. Thanks for letting us know. We will... Well, that's a good point. Maybe we should go and check out what we can do with times. But although right now we seem to have fixed the time fairly well, at least you can see it afterwards too. And at least you're here. More questions. That's interesting. So Caleb has asked a question. And this question, I think, won't necessarily have a nice answer, but I'm curious what the answer is. I want to know. You're saying if I have x over a plus a over x equals b, solve for x. Okay. First of all, if x is 0, you're in trouble. So we won't have to, we should not worry about 0, because obviously I can't divide by 0. We also don't have much time left on this live stream, so I'll just do this one quickly. The way I would think about solving this for x is I would first multiply through by x, and let's also multiply through by a at the same time. So I get x squared plus a squared equals abx. So I've just multiplied by a and by x on both sides. Now what I'll do is I'll turn it into a quadratic equation. X squared minus abx plus a squared is equal to 0. Now I actually have a quadratic equation, because this is just a number, and this is just a number. Because you're saying that somehow a and b might have been fixed beforehand. Maybe a is 3, and maybe b is 5. But there's some numbers. So once you have this, now it becomes this quadratic formula. I mean, of course, you can also use another method of solving quadratics if you so desire, but I'm just going to go and put this through because it's fast, and I'll just put it here. So what's that thing again? Oh, we got to sing, right? Oh, wow. Negative this thing plus or minus the square root of this thing squared minus 4 times the first and the third divided by 2. Okay, that's your answer. This thing, which is kind of mysterious, there's no simplification. Well, I guess there is. I can divide out an a. I mean, I can factor out an a. ab plus or minus a square root of b squared minus 4 all over 2. And that's the best I can do. There's actually not going to be an easier solution for this than what we see here. So I think that's the answer to your question. It's not nice, but it is. I mean, there is an answer. What can we do? What's another question to end with? Let's see. Okay. So let's finish on this one with Sophia. How do you manage your time more efficiently, get distracted less, study efficiently, and go the extra mile and do what's right even when it's difficult? I think the first thing is just to take great pride in your work. I think this is something that I care a lot about myself, about other people that I work with. There's a certain thing which is like when you do something and it's like it's got your name on it, okay? Whether it's your homework or whether it's something that you release to the world, it's your reputation. There's a great thing of like taking pride in your work. So if you ever have decided that you are going to use your time to do a task, well, be proud of what you've made. Don't be like, yeah, I just kind of sloppily did this. That's like what you would do if you were like, I don't really want to do this project. Here, just go have this. But even if it's a project you don't enjoy, take pride in it. And if you do that, even boring things become interesting. If your project is called wash the dishes, take pride in washing the dishes. It's like somehow I want to make sure that when I'm done, I said it was going to be done and it's done. And that's a certain attitude I've taken in my own life. Is that if I ever go and say to someone, hey, I am going to do this, I'm going to do this. And I think that pride in your own work causes you to then be more focused. You'll be less distracted. You'll be able to do the right thing even when it seems difficult. Mainly because you're basically saying, I decided that I'm going to do something and your time is valuable. So if you're going to go and spend the time to do it, make it something so that afterwards people will say, oh yeah, Sophia did it. And whenever Sophia does something, it's done right. That would be my advice for the day. All right. Well, unfortunately, today we have actually hit the time. And that finishes all of our weekday live streams for this crazy week. I'll be on again tomorrow night at 8 o'clock p.m. Eastern Time. And there we'll be actually doing a Math Circle collaboration. We'll talk a bit about some math problems, and then we'll do some random questions and answers that aren't math problems like this, but are general questions. Maybe I'll see you there. If I don't, I'll see you next time somewhere. Have a good weekend.